people here. So should we start, or should we wait for some people to join? Will they be joining?
We'll start, sir.
Okay, sure. Okay, so welcome to this class on reliability maintenance engineering. So as part of this first class, we'll be again studying the basics what we stopped with the SQC, right? We studied quality control and improvement, right? So in continuation to that, your first module is actually designed based on the statistical quality control, or what we call as quality control and improvement. Okay, so in this, the first half or the second half is going to be entirely of the type of what we discussed in your last course, quality control and improvement. Okay, so the rest of the unit we will be covering with the advanced level of whatever we didn't study in the last quality control and improvement. We'll be continuing with that. So the first module, the first half is going to be what we saw in the last class, and it's going to be actually a revision of those concepts. Okay. So to start with, so in this module or the unit 1, what we are going to cover is the reliability definition, reliability function, graphical representation, priori and posteriori probabilities of survival, component mortality. We'll be covering about mortality curve, what is useful life, and some reliability indices, or what we call as reliability mathematics, such as failure rate, mean time between failures, mean time to failure, bathtub distribution, downtime, repair time, availability, reliability, allocation, and mechanical reliability. Okay. So what is the definition of reliability management? So reliability is a part of engineering where you are going to apply your scientific know-how, like the scientific knowledge of a component or of an assembly or as a plant or as a process at its own. Like for any system or a subsystem, we can apply our engineering knowledge or our scientific know-how to understand whether the product is performing the intended function for what it is designed. We know, like for example, a mobile phone is designed for calling and sending messages and other things, various other things. So for any component, whatever is designed, whether it performs its function for what it has been designed, so that is called as reliability. Okay, so now what happens, sometimes that they tend to failure, okay, or tend to failure due to different reasons. But here I mean the failure at the given time. So reliability is one concept where we always talk about the reliability or the failure rate of the product with respect to the time what you're studying. Okay, so I think the same examples we saw in the last QC, right, the quality control and improvement classes. So what I'm trying to define is, so whether the product is able to perform at the time when it is required, and when it comes to performance, it's about the intended function for what it has been designed for. So that is what we call as in reliability. Again, this component will be operating or installed or operating in the specified environment for which it has to be designed. Say for example, a oven has to perform in a high temperature mode. Your refrigerator has to perform in a cold environment. So the surrounding environment or the inside environment for what it has been designed, we call that as reliability. And for design, and this component should be able to deliver that functionality in that environment. Okay, whether it's a whether it's a hot or cold or whatever it is, it has to perform. Okay, so that is what we call as the reliability of the component. So when I say the basic elements of reliability, it has 4 important elements. One is called as the probability. Then we have this adequate performance. Okay, so I mean, reliability is often confused or often interpreted in 4 different ways. One is called as the probability, like the chances of failure or the chances of success, what we call as the probability. The next word what we are seeing is called as adequate performance, whether the product is delivering its performance for what it has been designed for, or under the satisfactory level. So that is what we call as adequate performance, whether my component is performing in the correct perform correctly when I need it, or whether it's delivering is performance in the correct time when I require it. That is called adequate performance. Okay, if my engine has to run at an RPM of 1000 RPM, whether my engine is able to run at the 1000 RPM, that is called as the adequate performance. Then duration of adequate performance, like how long it is going to run. Like we buy a car and we assume that the car will run for 15 years, and if this 15 years is considered as a duration, and in this 15 years whether my car will run continuously without any um, uh, discrepancy in its performance, like it'll give the same performance throughout the lifetime of it, or towards the promised lifetime of it. Like that's what we call it as a guarantee or warranty, right? Where we talk that where we speak about the duration, right? So they normally give for a mobile phone they give a warranty of 1 year, or for any electronic gadgets is issued that they give you a warranty of 1 year, assuring that the product will have a adequate performance in that 1 year. So within 1 year, if something is happening to that mobile phone, they will be giving you a chance of free warranty or guarantee will be there. So that is called as adequate performance, right? For how long my product can perform without any discrepancy in its performance. That is called as a duration. Okay, so I still remember that we had a fan from Orient, which was running for a long, more than 20 years without any changing of coil or motor or anything. Only the paint got disturbed, so we have to just repaint it. And that means what the duration of adequate performance of that the ceiling fan was considered to be around like some 10-20 years. Okay, then we have operating conditions. Sometimes we operating condition is subjected to based upon the performance or where the environment where it has to perform. Say for example, you are having hair dryer. This hair dryer has to perform in any type of environment, right? So the operating conditions, or you're putting a what do you call it, a pump in a chemical plant, or a pump in a factory. The pump has to perform even though the surrounding temperature of that, if it's near to that some boiler or that, even understanding that it has to perform. Like it has to satisfy the operating conditions for which it has been performed. Say for example, some places if you take a street light, it will be running continuously without the switching off. Even after, if it is going to be put in such an environment, it has to understand what environment it has been designed, and it has to deliver its functionality. We will also discuss that in detail in the upcoming slides. Okay. So now let's take up the definition of probability. Now, first definition we are seeing the definition of probability in terms of mathematical terms. We also know, if you study the concept of probability and statistics, we know that probability may be defined as a likelihood of occurrence of a given event. That is, how what are the chances for an event to occur, whether it's a success or failure. What is the chances for that to occur? We call it as probability. So in mathematical expression, we express probability as the total number of ways an event can occur divided by total number of occurrence possibilities. Okay, that is how many number of times this is going to occur. So like how many number of times the event will occur, and in that occurrence, what is the chances of failure or success. So that is what we call as probability. Okay, normally in school days, or normally in your probability statistics class, your professor or your teacher could have talked like this: the number of chance of getting tails or hits. Okay, you're tossing the coin for 20 times. That will be the number of occurrence possibilities. Okay, so how many number of times you're going to toss a coin, that becomes the total number of occurrence possibilities. In that 20 times, how many times you're able to get a head or tail, that is called as the number of ways an event can occur. Number of ways you get a head, number of times you're going to get a head or a tail, that is called the number of ways an event can occur. Okay, so that is called as probability. And as I always used to say, the answer to this probability, or the value of probability, always be equal to, will be between 0 and 1. It will not go in negative, or it will not be more than 1. Why? Because we assume that 0 is 0% and 1 in probability means 100%. So never a system will have a probability of more than 100. and never it will have probability in the negative direction. So that's why we say that the probability of getting, say for example, in for 20 times if you're tossing a coin, in all these 20 times, if you're able to get in now you're going to answer this question, just follow me. The pro what, to make it explain this probability. Okay, you're tossing the coin for 20 times, that is the total number of occurrence possibility is 20 times, and I'm telling you, in all this 20 times whenever you're tossing a coin, you're getting hits. Okay, hits, that is total number of ways an event can occur. So when you toss 20 times a coin and all 20 times you're getting hits, hits only, so what is the probability of your you tossing a coin? Are you able to understand? 20 times you're tossing a coin and all the 20 times you're getting hits only. So what is the probability now?
100%, sir.
100 percentage. So in probability, we call that as the probability is 1. 1 means 100 percentage. Okay. So that, and what is the probability that if you're getting 20 times you're tossing a coin and only 10 times you're getting the hits?
50%, sir.
50 percentage. Okay. And you're tossing a, yeah, so that is what we call as probability. Okay, so that means what, it has a precise meaning of interpreting. So that's why we call it precise. Probability means preciseness. Okay, all the precise is more. Okay, for example, probability of 0.95 means, 0.95 means what, you have 100, for example, if you have 100 items, 95% of the items is performing very well, and only 5% is what now here, out of 100 items, if you get a probability of 0.95, that means what? Only you have failure of how many items?
5%.
5% or 5 items. Okay, so that is what is called as probability. And one important thing is that I always told you, probability means it's about the under or the reliability is always we calculate under the under at which time or in what time, that is a stated time under stated conditions. This wording is very important here. So here yeah, I like to underline this, at the stated time under stated conditions. That is very important. So these two words are very important. Okay, stated time is what, at a given time, at the given conditions. Okay, so given conditions may be the conditions in which the or the environment in which the component is performing. In that environment, at a given time, what is the performance. So that is what we're calculating in this probability. So even reliability is the, I told you, probability is also a word which we use in reliability. The definition also carries the word probability. Okay, so now we understood what is probability. Again, in probability, again value can be only between 0 and 1, and the probability is always calculated at a stated time or the given time and the given conditions. Okay. So next we saw the word, what is adequate performance. Adequate performance is what it is expected out of your product. For example, we have a thermometer. The thermometer should do what? It should show the temperature of a if it's a basic thermometer, it should show the temperature of the human body. Okay, and we know how it is performing, and we expect that the thermometer to show the reading whenever we require. You have what do you call it, a fuel gauge in your vehicle. The purpose of the fuel gauge is to show the quantity of fuel that is available or left out in your in your petrol tank or in your vehicle. So it has to perform for what it is expected out of your product. We always have this example. So if example, if you have a 5 ampere fuse in your electrical system, and what is the fuse has to do? The fuse carrier has to do. If the current supply is more than 5 ampere, the fuse should blow off. Correct? If it continues to run, even if the even if the power supply is more than 5 ampere, what will happen? If you're installing a fuse in your electrical system to ensure that if the power supply is more than 5 ampere, it should cut off or it should blow off. Okay, but if it continues to run more than 5 ampere, if it's allowing the power supply to pass on to the electrical system, what will happen?
can control safety, sir.
It is going to it is going to lead to some failure of the system, or sometimes it is going to cause a major catastrophic effect on the people, or its safety becomes a question, right? So what we are expecting is, even though the fuse is going to fail, it has to fail ensuring that the uh, performance for what it has designed is it is performing. Okay, so it's not like the fuse should be safety, fuse should not blow off, fuse should get flow blow off, because that is for what it has been designed. So that is what we call as performance. Okay, next, the duration. The duration, the period for which the performance of the product is satisfactory. Like that's what I call for how long you are able to run the product. So that is what we call as duration. So after you install a product, always a product is subjected to some wear and tear. Okay, so hence we have to define the duration for which the product can run successfully, but at the same time that is satisfactory. But at the same time, the product should also deliver its performance during that time. Say for example, we all have some two wheelers, or we used to have a two wheeler. Okay, so this two wheeler will have some tires. So the tires, what is the lifetime of the tires? Normally how they predict, depending upon the kilometers what it is running. Okay, so if for example I have designed a tire I have bought a tire which can run for some 1,000 kilometers or 2,000 kilometers. If I'm running this, if I'm still continue using these tires more than my 1,000 kilometers or 2,000 kilometers, what will happen? The tire is going to fail. But the tire is designed to perform well for 1,000 kilometers. Say for example, I can drive my vehicle for 1,000 kilometers in 1 month. In 1 month, I'm driving my bike for 1,000 kilometers. If I'm using my bike a lot, if I'm riding it for a period of 1 month, that means what? In 1 month, I should drive 1,000 kilometers. So in that 1,000 kilometers of driving, the tire should not give me any problem. Even though there is going to be some wear and tear, if even though it's going to have some wear and tear, but the performance of the tire should not be affected in that 1 month. So that is what we call as adequate performance, or adequate duration of adequate performance. Sometimes we buy lamp in our house, a tube light or something. Okay, so this tube light is designed to run for, say for example, some 10,000 hours. For this 10,000 hours, the product should be performing very well without affecting its functionality or without getting failure. But if the bulb is failing before this 10,000 hours, that means what? It is not running it correctly, or it is defective product. So that's why the duration of adequate, how long the product is going to perform well, delivering its full functionality for what it has been designed, that we call as duration of adequate performance. Okay, hope you are able to understand. Next is operating conditions. Operating conditions is the environment. I'm talking about the environment in which the product is expected to function adequately to the stated product life. Okay, that means what? For the promised period of time, the product should deliver its full function irrespective of the environmental condition, because any product is designed for a environmental condition which it has to perform. Considering the environmental condition or environmental conditions, or the operating condition is also a constraint in designing the product. Okay, so if we want to design a product, or design a material for a boiler, you should take into consideration the boiler temperature, and only you're going to design the product or choose the material for the product. So what we are expecting, if it is going to be used inside a boiler, the temperature of the boiler should not affect the item or the product. um, so that's how it is designed, right? So basically what we're expecting, even though at a high temperature, the product should function and deliver its functionality for at least for the certain period of time. One example is we have air conditions. Of course, the summer has started everywhere. So we are in India. So what we are trying to do, we are trying to use a air conditioner. So normally, what will happen is this air conditioner will perform. The performance will be very good in hot and cold, hot climate or dry climate. But when the climate is so wet, what happens? It is not performing accurately to what it has been designed. And again, when you have a shock absorber, okay, if you're riding the shock absorber in a good road, like Bangalore to Chennai, you don't feel any, or at least from Bangalore to Vellore, if you're riding your motorcycle, the road is even and you don't and the shock absorber will continue to perform for a very long time. But imagine if you're driving the motorcycle in an uneven road. Say for example, you are driving the road in some what do you call uh, rough roads. What will happen where uh, more bumps are there? What will happen? The lifetime of the shock absorber will be not as what it is expected. But this shock absorber are designed to provide some damping whenever you're riding a bike in a uneven surface or uneven roads. So the shock absorber function is to provide a good damping or provide a cushioning effect to the rider, right? So but the lifespan becomes a question mark. That is, for how long, if you continue driving a flat, smooth road, the lifetime of the shock absorber is going to be for a very long time. But if you're driving your bike in an uneven surface or an uneven road, what happens now? The lifespan, or for how long the lifespan here, I mean the longevity of the shock absorber. The longevity of the shock absorber now becomes a question mark. Okay, so that means what? The rate of failure, the chances of failure when a shock absorber is used in a uneven or a unsmooth road, the lifespan of the shock absorber will reduce than when you're using it in a smooth road. Okay, that's why. So the operating conditions also plays a very important role, and the product is expected to deliver its full functionality for the stated product life, or how many duration or how long the product can deliver its functionality. As per the guarantee what you are giving to the product, it should be delivering that with respect to the operating condition where it has been for what it has been designed. So that is what we call as operating conditions. So now we saw what is probability, then we saw what is adequate performance, then we saw what is duration of adequate performance, then we discussed about the operating conditions. Okay, so that's what all this items which reflects the definition of reliability. Now let's get back to the original definition of reliability. Reliability. So now from our understanding, what we can how we can summarize the definition of reliability is: reliability is generally defined as the ability of a product. Now look at the words: ability of a product to perform as expected over time. Okay, to have a more refined definition of reliability, formally we can define reliability as the probability. That probability is the first word what we study, right? So the probability that a product, a piece of equipment, or a system, or it can be anything. What I mean is it can be a product as a whole, or a piece of a product, or a system. Okay, the probability is what? The some probability is the chances of survival. Okay, your equipment, your product, or a piece of a product or a system performing. Here I mean the performance. It's what? Performance of what? Its intended function. Performance of what? Performance of its intended function for for the stated period. Stated period is what? The time. At the given time, what is how was it performance? Under what? Under the operating conditions. Okay. Probability of what is the product or the piece of the equipment. Performance of what? Performing its intended function for the stated period of time for the specified operating conditions. So that is the definition of reliability. Okay, so please note on this definition of reliability: the probability of your product, a piece of equipment, or a system performing its intended function for a stated period of time under specified operating conditions is what we call as reliability. Okay, so hope you can hope you understand what is the definition of reliability. Now slowly let's get enter into the need for reliability. Okay, now what we are speaking about, we started speaking about reliability. Now we know what is reliability, the definition of reliability. And now let's discuss for some time what is the need for this reliability management, why it is needed. So reliability here, I mean reliable operation of critical equipment. Okay, because some life-saving equipments are there, or some safety equipments are there where its reliability of operation is it should be ensured by us, because otherwise it's going to lead to a lot of failure or a lot of catastrophic effect. Say for example, you are having a ventilator, and if the reliability on that ventilator becomes a question mark, or when it is required, it has to provide oxygen supply to the patients. And if the reliability of that critical equipment, life-saving equipment, ventilator, becomes a question mark, then what happens? The patients are going to lose their life. That's why reliability of operation of critical equipment is very important. That's why this study of reliability is also becoming an important. Then, if you know the reliability or the chances of failure of your product well in advance, what we can do is we can plan for maintenance activity. Say for example, there is a built drive which is connecting two motors, or a or a motor to your pump. If that belt drive is failed, or we know that the belt is subject to wear and tear continuously, and if you are expecting the belt to failure by the end of this month, well in advance you can plan to procure a new belt and wait for, and you can replace the belt immediately without affecting the stop time or the downtime of the machine. Okay, you're having if you're having a cycle, and the cycle has a chain, right, which connects the gears. Okay. And the back tire and the this one, right? So if the chain is loose and you expect the chain to failure, what you can do, you can take your bike to the repair shop, cycle repair shop, and you can refix, or you can tighten the whatever the maintenance activity you can do. You can plan the maintenance well in advance if you know the reliability of the product well in advance. And as I always also discuss, when you know the reliability of your product, it is going to ensure the safety, right? There are, as I told you, there are some critical cases. Say for example, there is a hook in a crane, in a crane, a movable crane. There's a hook, and that hook is defective, or the hook is not connected very properly to the crane. So what will happen if it is not good? We should suddenly replace this, right? Say for example, if you're having a if you're traveling in a aeroplane, or you're doing a bungee jumping, there is always a parachute, or a hook that is being attached. If you're doing a bungee jumping and there is a hook, right, that is connected to your body, the rope is connected to your body by some hooks. Imagine the hook is not functioning and you're doing a bungee jumping. What will happen? Your life is dependent on that one single component of the hook. And if the hook is failing and you're doing a bungee jumping, it is equivalent to committing a what? What? You're doing a bungee jumping, the hook, your life is dependent on the hook, which is connected to the rope, and if the hook is not functioning properly, it is equivalent to committing a suicide, right? So that's why reliability of the product is important to ensure safety. Then comes the last important factor: improve quality of an item. Okay, it always tends to improve because if the reliability of the process or the product is not good, that means what, the quality of the product is defective. So to improve the quality, the study of reliability is very, very important. So that's why reliability is required in many cases. One such example, in India has a very good record of record in all its space mission. But initially, what you see, um, so let's go from down to top. Say in August 1979, we launched a Rohini satellite, but we are not able to place it in the orbit. Similarly, in 1987, we launched ASLV Servo SS1. We failed. In July 13, 1988, we launched ASLV S Rose 2, but we are not able to place it in the satellite. Again, in 1993, we developed a PSLV. Again, we failed. In 2006, GSLV we launched. We are not able to place it in the orbit, and the rocket also fell in the sea. In April 15, 2010, we launched GSLV D3, but it also fell into the sea. In December 25, 2010, we launched GSLV F06. Again, it failed. So if you trace the track record of our ISRO from 1979 to 2010, it was almost failures. Okay, only failures were the result. But post 2010, what happened? You know, right? So now we are able to launch complete the moon mission Chandrayaan, and we are able to land on the south pole of the moon. Also, we have launched a satellite to study the what do you call the sun itself. So that is the advantage of that. But so failure is common, but what is that? We should learn from the failures, correct our mistakes to be more successful. So this study of failures is very important. The study of failures is what I define it as. To study the reasons for the failure is what I call as a reliability. Okay, so this reliability is very important. So what is the three main tasks of reliability? Here we are trying to study the existing system in detail. First, we are taking a system, we are studying it in and out, we are studying each component very carefully, and we are coming out of to have a very good understanding of the system. We are first carrying out the initial system level study. Then we are also studying the possible ways of increasing the reliability of the product under examination. So first you're selecting a product, you're selecting the product in and out, and you're coming out with a detailed study or understanding of the product. Next, what you're trying to do is you're trying to uh, uh, finding the chances or the ways of increasing the reliability of the product. Like how can I improve the reliability? Whether I can have a parallel run system, a standby run unit, or whether I can do any preventive maintenance well in advance to increase the reliability of the product. All these things we are going to do. The third point is to maximize reliability for a given conditions or parameters. Because as per the definition of reliability, we know that it's also about the operating conditions in which the equipment has to run or function. So that's why reliability conditions is also to maximize the reliability for a given condition or parameter is also very important. So these are the three main tasks of reliability. What are they? To study the existing system, then to come out the best way of increasing the reliability of the system, and the third is to come out with the uh, third is to propose the chances of maximizing the system reliability under the given conditions and parameters. That is very important. For this conditions or for this parameters, how I can increase the reliability of the product. So that is very important, right? So that is called as the task of reliability. Okay. So now let's see some of the other indices or what I call the parameters of reliability. The first is called as the repairable items. So this understanding of repairable and other things what we are going to look forward in this class is required for you to understand the later concepts of MTBF or MTTF. So let's try to understand the first concept, repairable items. A repairable item is one which can be put back in service economically. So here I stress on these two words, which can be put back and service economically. Okay, what is this service economically? Like if my cycle tire is getting punctured, I can repair or I can fix the puncture, and that is economical because fixing a puncture in recent times could cost you around 20 rupees or 30 rupees, but it is worth doing that, correct? So whenever you are able to repair an item and put back the product back to its original state, and if that is then we call it as repairable items. So what is that? If you're able to repair a product or an item, and if you're able to put back the product into its original state of function, and if that process is more economical than buying a new product, then that is called as repairable items. Okay, say for example, in a repairable systems, failure can occur any number of times. Irrespective of the number of failures, it should be worth to repair it and run it for a long time. Example, engines of an aircraft can be repaired, cameras can be repaired, all automobile machine tools, etc. They can be repaired. Okay. So the items which can be repaired in an economical way, and after repairing, if it is able to function for its defined functionality, that is called as repairable items. And this repairable items failure can occur any number of times. So this is very important for you to understand. You should understand this wordings as well. In a repairable system, the failure can occur any number of times. Okay, I will say you why this line is very important in the coming slides. What I'm saying, in repairable items, the number of failures can be any numbers. It can be, the failures can occur any number of times. Okay. Next, if I have a repairable item, that means what? I am also going to have a non-repairable item. Okay. So a non-repairable item is one where the failure, once the failure has happened, it is not worth enough to repair the product, or it is not even possible for us to repair the product. Okay, I told you about the tires. The tires, you can fix the puncture. If it's a puncture, you can fix the puncture and you can run it, and the tires will perform as they used to perform previously, and that is economical as well. But imagine if a tire has blasted, the tire is completely blasted. Now what happens? It is not even possible for us to repair it. So now and if I want to repair the tire, it won't be able to deliver its original functionality for what for what it is intended to by design, or the repairing for a blasted tire, it is more costly to repair. So now that becomes a non-repairable item. For example, a light bulb is there, a small bulb is there. If it is fused, we call this, bulb is fused. If the bulb is fused, it is very difficult and it is not cost effective to fix it and again run it. For example, a transistor. If a transistor is repaired, it is totally gone. It's a small component, a transistor. If it is gone, it is very difficult for us to repair it, and it's not cost effective also, because a transistor maybe costing less than a rupee, and it is unnecessary for us to spend more to repair the transistor. Rather, we can replace it with a new transistor. Or again, a spacecraft, once it is launched, it is very if you launched a spacecraft, and if you put it in a right orbit, and if it's malfunctioning, it's not possible for us to go to the space, repair it, and make it run. Rather, we can launch in, for that cost, it is very advisable to launch a new spacecraft itself, right? So that's why some items which you can't repair, and even if you're repairing, that is not cost effective, and that is called as non-repairable items. That's why I say that in non-repairable items, the failure can occur only once. Okay. Again, I stress on this point. In a non-repairable item, the failures can occur only once. In a repairable item, the failure can occur. In a repairable system, the failure can occur
Many times, sir.
many times. Very good. In a non-repairable item, the failures can occur only once. Okay. So that is the difference between the repairable and non-repairable items. Okay, now let's go slightly enter into the math behind this. Okay, so now I told you reliability is always defined with two parameters, that is called as probability and time. Okay, so now let's get deeper into the definition of this reliability. Okay, so the probability of your product surviving, probability is what? The chances of a product to survive in a given time or until time t. Okay, here I use the word probability of a product. Probability and time. Okay, probability and time. Here I'm talking about the probability and time. Okay, so if your product is able to survive until time t, then we are using this formula, reliability at time t. Okay, the reliability at time t. Okay, so what is that? Reliability at time t. Okay, reliability at time t is equal to what? E power minus lambda t. Now please note down this formula. Whenever I'm giving you some formula, please note it down in your notebook, so that when we are moving to solve the problems, it will be very easy for us. Okay, so here reliability at time t is what? E power minus lambda t, and this expression is called as a exponential distribution. If you're not very good at math, don't worry. Just for this point of time, we'll forget about the exponential distribution. Okay, so now reliability at time t is what? E power minus lambda t. Just make a note of this important formula, which you'll be using throughout this course when we deal with reliability. So reliability at time t, so reliability of a product at a given time t is equal to E power minus lambda t. Okay, here the letter lambda or this lambda here means what? Lambda means here the failure rate, e power minus lambda. Lambda is the failure rate, t is called as the time. Okay, so have we noted it down?
Yes, sir.
Okay, so again, when I was discussing about the definition of probability, I told probability or the probability can exist only between 0 and 1. Okay, so we saw some examples of tossing a coin. Okay, the probability can be 0 or probability can be 1. Same applies to reliability. Reliability of a product can also be only between the values of 0 and 1. In your examination, when I ask you to calculate the reliability of a product, if you are giving your answers in more than 1, that is not possible, first of all. And if you're giving an answer less than in negative value, then it's like that. You should recheck your problem, you should revisit your problem and check the calculations again. Okay, that's why reliability of time t is equal to e power minus lambda t value cannot go less than 0 or more than 1. If your reliability of product is more than 100 percentage, that means what? You're running an ideal machine. An ideal machine never exists in this world. That's why the reliability of a product at a given time t is cannot be go the value cannot be go beyond 0 or more than 1. I mean less than 0 or more than 1. Okay, so that's why I told, again I'm telling you, reliability will always give you should be the answer should be more precise. Even the zeros count here. Okay, so if I say the probability of the product is 0.95, that means what? 95 components out of 100 components, 95% of the components are surviving under what? Under the under the stated time and stated conditions. Okay, so at a given time, at a given condition, the reliability of the product, reliability at time t is equal to what? E power minus lambda t. Here lambda denotes
Failure, sir.
failure rate. Very good. So now it's important for us to understand reliability at time t. Okay, just one more thing we are adding. So if we are going to have a very large number of items to be tested for a given time t, then when there is more number of items, okay, when there are more number of items for which you have to calculate the reliability, you can use this formula. Reliability at time t is equal to number of items put on test at time t equal to number of survivors at time t equal to 0. Say for example, whenever you're starting a you're going to test 100 components. Okay, let's assume we are going to test some 100 components. Okay, and I'm asking you to test the reliability of the product after 10 hours. Okay, now understand what I'm telling. Let's assume you are going to test 100 components. How long you're going to test? You're going to conduct the reliability test after 10 hours. So now the number of items put on test at time t is what?
10 hours.
No, number of items. Number of items initially how much I'm putting in? 100.
100.
Now I'm telling number of survivors at t. That is after when t equal to 10. What is the number of survivors? Out of this 100 bulbs, how many would have survived after 10 hours? Okay, so that is the question mark here. So initially when you start the test, how many number of components you are putting in? When t equal to 0, okay, when t equal to 0, what is the number of components that is participating in the participating in this reliability test? That is when you're starting the test, how many number of components are there? Are you getting my question?
100.
100. Very good. So when you're starting the test, there are 100 components. After 10 hours, how many number of components will be there?
10, sir.
After 10 hours, how many number of components can survive? Depending
10.
upon it, it need not be 10. It need not be. It's not like that. I'm just giving small n. Small n is the number of survivors. For example, if I assume if small n is denoting the number of survivors, initially when t equal to 0, n is equal to 100. So the reliability of the product when you start the test is what? Reliability of a product when you start the reliability test is what?
100.
100 or what? In reliability, how much? How should you call that? You should call it as 100 means what in reliability?
1, sir.
1. Excellent. So this time when you start the test, all 100 items are present, all 100 items are surviving. So that's why the reliability of the product is 100. But after 10 hours, you put 100 components. Out of this 100 components, let's assume that some 60 components only survive. Okay, only 60 components are survived. Now what is the reliability? After 10 hours, only 60 components survived, 40 components failed.
0.6, sir.
0.6, right? So that is what we call as reliability. So now always this is very important. So 0.6. 0.6 means what in percentage?
60%.
60%. Okay, so my job is done now. So at time t, the number of survivors is equal to what? At time t, when time t is equal to 0, the number of survivors is what?
100, sir.
100. So that means what? Reliability of the product when t equal to 0, when t is equal to 0, the probability of survival, the reliability of the product is what?
1, sir.
1. 1
1.
means what? 100%.
100%.
100%.
So are you able to understand this? So that means what? When you start the test, always the reliability of the product is 1. Because when t equal to 0, the reliability of the when t equal to 0, the reliability is what? 1, or what we call as 100%. But after some time, let the time is being 10, 20, 30, whatever it is, as the time passes, or when the test reliability test starts, what happens? The system will start functioning, and some lot of failures or wear and tear can happen. And for that wear and tear after wear and tear happening, we are going to calculate the number of survivors after the given time. So after the given time, how many survived? In our case of example, we assumed that the number of survivors at t equal to 10 is how much? In this example, what we discussed, t is equal to t 10. When t is
10,
10,
sir.
what is n? 60, right? So that's why we got the reliability of the product. That is means what? Reliability of the successful survivors were what? 60%. Okay, so that's how we do the reliability testing. Okay, so next we see the next definition of next one more definition we are showing. That is called the redundancy. Okay, redundancy means the possibility or the existence of doing things more than one way. Okay, so say for example, um, in your class there are many. If you, for example, if you're doing any mathematics course, you'll understand this. There are more than one way to find a solution to your problem. Okay, because say for example, uh, uh, say some people will understand. I think you'll understand this thing. There are more than one way to solve your problem, even it's in a life, in our own life, or it's in a mathematical uh, problem. There are more than one ways of solving a problem or finding a solution to your problem. Okay, so but the method of doing or method of finding a solution to your problem need not be identical. If I give one question, one mathematical question to two of your friends, to you and your friend, you both can get a correct answer, but the procedure what you approached, the procedure what you adopted to solve the problem may not be similar, may not be identical to your friend, right? Are you able to understand? I'm giving two problems. I'm giving one problem to two friends. Each one can, everyone or this both friends can get the same answer, but the procedure what they adopted to solve that problem can be different, or cannot be need not be identical. Okay, for example, there are two, I mean, say for example, I want you to travel from your plant to Vellore, or to Krishnagiri. For example, let's take like that. I want you to travel from your company to Krishnagiri. One can take the route through Atibali, the other one can travel through Adiyaman Kotte, that road, and reach Krishnagiri. So to reach a destination, there are two routes. Okay, but the destination is what? There is a destination is
Single place only, same place.
sorry, I'm not able to hear you. The destination is one.
Same only, sir.
Okay, in our case, the destination is Krishnagiri, but to reach Krishnagiri, there are two different routes. So whenever there is a possibility, or whenever there is a chances of reaching to a solution, or reaching to a problem, addressing a problem in more than one way, we call that as redundancy. Okay, and this redundancy means what? That there are multiple ways to solve a problem, or to address to provide a solution, but these two ways of doing it, the two approaches, or two or three approaches of doing finding a solution to a problem need not be identical. Okay, that's what you should understand. Okay. Next, we have something called as active redundancy. So what is active redundancy? Active redundancy is one in which all redundant items are operated simultaneously, instead of switching on only when a need arises. Okay, that is what both redundancy means two ways of doing a thing. This two ways of doing a thing is always active. That is, they are live. Okay, it's not that only one failures the next will start. It's not like that. At any given time, these two systems are live. Okay, these two systems are live, but even one is when one is failing, when one way of finding a solution to a problem fails, the 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 remaining one will automatically takes its position. Okay, say for example, I'm giving you one example here. You're using a desktop. For example, you're using a desktop, and what happens when you're using a desktop? You're using a power source from the main power supply to your house, and immediately when your house, when there is a power shutdown by the power supply board, there is a power cut. So what happens? Automatically the UPS in your home takes the position of the regular power supply, and it ensures the effective functioning of your desktop. Are you able to understand? So that means what? The UPS is also live, the main power supply is also live. When the main power supply cuts, the UPS takes its position. Correct. So this is what we call as active redundancy. Are you able to understand this active redundancy?
Yes, sir.
Okay. Next, what we call as standby redundancy. Standby redundancy is what? There are two redundant items, but this one redundant item takes the position of the previous one, which is live. Here, the second one is going to be in standby mode. This is not live. Only when it is required, you are going to switch it on. Okay, so the standby redundancy is one in which the alternate means of performing the function is not operated until it is needed. The second, the alternate system is switched on only when the primary units fails. Right? Say for example, there are two systems. One system will be continuously functioning. Okay, there's a primary system and there's a secondary system. The secondary system is what I call as a standby system. Okay, try to understand there are two systems. One is the primary, another one is called as the secondary. The secondary is also known as standby system. Okay, so when the primary system fails due to some reason, the secondary system or this standby system will be switched on, or will be put in the place of primary system only when it is required, or only when the primary system fails, the secondary system will be put into the place. So here, out of these two systems, the primary system is always live, and the standby system or the secondary system takes the place of the primary system only when it is required. For example, let's go back to the old example which we discussed. Imagine you, instead of UPS, you are having a generator in your home. You're using a desktop, and suddenly what happens? There's a cut down in the power supply from the main source. So now what you're going to do? You don't have a UPS, but you have a generator. You will go to the generator. You will switch it on. Okay, you're going to the generator, and you're switching the generator on. So that means what? The generator is a standby system here, and it takes the place of the main source or the primary source, primary system. So that's what we call the generator as a standby system. Or in case of a four-wheeler, you're driving a car for a long distance, and always in car there is spare tire, what you call as a stepney tire. Okay, so when any one of the tires of your vehicle fails, this stepney tire takes the position of the primary tires. Like the front or the rear tire, the rear left tire has gone. You can take the stepney tire and put it in its place. So that means what? There is always one backup system which is there to support it. This backup system is always we call as standby system. So since this is another way of doing the thing, we call it as redundant system, or what you call as standby redundancy. Okay, so now we are able to understand standby redundancy. Okay, are you able to understand standby redundancy?
Yes, sir.
Okay, so now see what is failure rate. Again we are increasing one by one. So what is the formula to calculate reliability? What we discussed, R of T. R of T means what? Reliability at time t is equal to e power minus lambda t. So this is the definition what we know for reliability. Now this failure rate is denoted by the Greek. The failure rate is represented by the Greek letter lambda, or we can also use the letter z. Okay, so we can use z or lambda. So this both denotes reliability. Okay, so failure means what? Failure means termination of, or the ability of a product from doing its required function, right? So the product is intended to function for a, or to deliver a functionality. Okay, your mobile phone is used for talking and something. If this mobile phone is not allowing me to talk or send messages, that means what? The functionality is not delivering. It's not delivering its functionality for what it has been designed, and the phone is failure. Now it's a failure. Okay, when a component is not useful, or not anymore useful at and it's not able to deliver for what it has been designed, then I call that as product as a failure product. So mathematically, how I can represent is like this. Here I use two words. Here NF means number of failures. Okay, NF means what? Number of failures. NS means what? Number of survivors. NF is failures. NS is number of survivors. Survivor means what? After some time, how many numbers of items or you're testing, or how many number of products you're testing, out of number of products you've tested, how many are able to survive, or how many are able to live. That is called as number of survivors. Okay. Here I use the word lambda t. Lambda t is what? For example, when you are starting the test, t value will be, when you're starting a reliability test, what is the t value?
0.
0. When say when in our last example we tested the components for how many hours?
10 hours.
10 hours. So now what is lambda t? Lambda t is called as a change of time. Okay. So now lambda t is what? 10 minus, that is if you assume initial and final. Okay. So if initial time is 0 and the final time is 10, what is delta t? Delta t is t of f minus t of I. So that means what? Delta t is 10 minus 0 in this case. Okay. Now I want to test my component for 20 hours. From 10 to 20 I have to calculate. So now t of I will become what? I want to test my component from 0 to 10 one test I'm going to run. Then from 10 to 20 I'm going to run another test. So now for the second test, what will be the t of I value? What will be the ti value for the second test? First test I'm going to run from 0 to 10. That is 10 hours. First 10 hours I'm going to run one test. Second test I'm going to run from 10 to 20. So what will be the t of I value for the second test?
10 only, sir.
10. What will be the tf? Tf value will be a what?
10 divided by 10, sir.
No. Just understand. What will be the tf value?
20, sir.
Tf value will be 20 because it is second test. So now t of f will become 20 and t of I will become 10. So now what is the value of delta t?
10, sir.
10. Okay. So that means what? So now this denotes what? Delta t is the duration for which the test is being carried out. Okay. If when t of first case, when t of I is equal to 0 and t of f is equal to 10, delta t is 10. Similarly, when t of I is 10 and t of f is 20, then the delta t is 10 because we have taken in such a way. Or okay, because we have just assumed 10 increment only. But if t of I is equal to 10 and t of f is equal to 30, what will become to delta t?
20, sir.
20. Good. That's how you should calculate delta t. Okay. That means what? The reliability test is conducted for 30 hours. Or the reliability test can be conducted for 10 hours. Or 10 incremental hours also I can conduct. So that's what we call as failure. That's how we should calculate the failure rate. So the formula to calculate failure rate is lambda t, failure rate at time t, failure rate at time t is equal to nf divided by, the nf is what? Number of, what is nf? What do you call this nf? Number of
Failure, sir.
failures divided by, what is ns?
Number of survivors.
Number of survivors. Okay. Okay, so that is what we call as, that's how we calculate failure rate. So this formula is very important. Please make a note of this formula. Okay. So when you know this, what happens when your product fails? Say for example, a hair dryer, you can throw it out. But when your product washing machine is failing, you can get it repaired. Why, sir? Why this difference is that when a hair dryer fails, you are throwing it out, or you're scrapping, you're making it as a scrap, you're putting in the scrap. But when your washing machine is failed, you're trying to repair that washing machine. Why?
Due to cost, sir. Errata is cost S and machine was cost nice.
Because costing. And again, what happens here? It's not worth enough when my hair dryer is failed. If I want to repair that hair dryer, the cost of repairing can be more than the cost of the hair dryer, or more or less equal. Okay, say for example, in a mobile phone, screen is very important. Okay, and if your screen is damaged, what you're trying to do, will you try to buy a new mobile phone, or you'll repair the screen?
Nowadays we are buying new only, sir.
Why? Because we find that for the cost of mobile screen, you can buy a new mobile itself. That's why some components cannot be repaired, or what you call as non-repairable items. Some items we can repair and reuse because the cost of repair will be much cheaper than the original cost of the product. That's why we always go for repairing the product. So that means what? These are repairable items and they are called as non-repairable items. So to decide at this, we need to know the failure rate of the product. So now I'm giving this to you. You have to solve this and give me the answer. If there are, understand the question and give me the answer. If there are 200 surviving components, if there are 200 surviving components, 200 surviving components means what? N,
Yes.
N, S. After how much?
400
400
seconds.
seconds. Here 400 seconds is what? T. Okay. 8 components fail. Here 8 components denotes what? Fail. That means what? This is okay. So till 400 seconds, 200 components were there. After 10 seconds, that is what? When t equal to 410, when t equal to 410, 8 components failed. Now they are asking you to calculate the failure rate lambda after 400 seconds. After 400 seconds, what is the failure rate? So failure rate of t is equal to what? N of f divided by n of s into delta t. Okay, now give me the answer. Okay, so now what happens? That's what lambda we know. Lambda we have to calculate. T is equal to 400. Number of failures is how much? Enough. Number of survivors we know. And what they say? After 10 seconds, that is lambda t. After 10 seconds, lambda t. What is the failure rate? So now it is what? How you got lambda t? T of I minus T of f. T of I is what? 400 minus T of f is how much? Sorry. T of I is how much? 400. T of f is what? 410. Because 8 components fail over next 10 seconds. Okay, 400 seconds after means what? 410th second. 410th second minus 400. So this will give you 10. Are you able to understand? So that's why we put delta TS 10. Okay. Are you able to understand?
Yes, sir.
Okay. So that's why we call that the failure rate of this component is 40 percentage or 4.4 0.4 percentage. Okay. Good. So how many, that means simply means what, 0.4% of the surveying components failing each second. So every second 0.4 components is going to fail now. Okay. So are you able to, will you be able to calculate the failure rate now using this formula? Using this NF divided by NS into delta T, you can calculate the answer, the failure rate. Okay. So next we have something called as the failure density. So what is failure density? Failure density is given by the letter FD, small f and d. Okay, it is what, the number of failures during a given unit interval of time. What is it? The number of failures during given unit interval of time. So that is number of failures. Okay, number of failures with respect to the given time divided by total number of items at the beginning of the test. So same thing, right? So number of failures, how many number of failures that has happened given an interval of time. Say for example, some 100 units are subjected to test. That is, initially there are 100 items that are subject to test. When you start the test, let's assume you are having 100 components. Out of this 100 components, how many number of failures has happened in a given interval of time? Say for example, given, let's say 10 hours. In 10 hours, how many number of components has failed? The first hour, let's assume 10 components has failed. In the second hour, some 20 components has failed. In the third hour, some 5 components has failed. In the fourth hour, some 4 components has failed. And fifth hour, only one has failed. And the sixth hour, some 20 components has failed. And seventh hour, again 3 has failed. Again 2 has failed. Again 9, again some 3 has failed. Again some 1 has failed. So every 1 hour I have conducted this test. That is, the total duration is that t equal to 0, t equal to 10. So in this duration of 10 hours, every hour the failures are noted, and initially how much units were participating? 100 units were participating. Are you able to understand? Or should I repeat? Or should I repeat? Are you able to understand? In the given interval, that is, I am going to conduct the test for 10 hours. In this 10 hours, every hour I have recorded the failures, what is happening. I am telling you the initial number of components were 100. When I begin the test, how many number of components were there? 100. In this 100, after conducting 10 hours of test, there are certain number of failures that is happening every hour. Okay, there is some set of failures which is happening every hour. Say for example, in first hour it is 10, second hour it is 20, third hour it is 5, fourth hour it is 4, fifth hour it is 1, sixth hour it is 20, seventh hour it is 3, eighth hour it is 2, and ninth hour it is 3, again 10th hour it is only 1. So now what is the failure density? Can we calculate? 10 plus 20, 30, 35, 39, 40, 60,
69, sir.
63, 63, 65,
69.
60, 68, 69. So 69 divided by 100. What is that?
0.69, sir.
0.69. Okay, so that is called function failure density. Next, we have something called as mean failure rate. Mean failure rate is what? The average we have to take. Okay, you can use the word Z, or you can also use the word lambda. You can use any one of this. So mean failure rate is what? Lambda 1 plus lambda 2 plus lambda 3 divided by t. T here denotes the hour. So totally 10 hours I have done. Okay, failure rate, here I denote failure rate at 0, at failure rate as 10. If my failure rate at first, when lambda equal to 1 is 2, here failure rate is what? Lambda means it will be like 0.2, 0.3, 0.1, so on and so forth. So here failure rate will always be in point value, correct? So that's why failure rate divided by total number of hours, how many hours I'm going to conduct the test. So that is called as the failure rate. Okay, are you able to understand mean failure rate?
Yes, sir.
Okay. So now after this, we'll see how to calculate the reliability of an item. Okay. So now how to calculate? So basically, as a generally what we are going to do is we are going to conduct a series of tests. That is, we are going to conduct a lot of reliability tests, and we are going to note on the number of failures. Okay. So then we'll be calculating lambda. Then we have to calculate the reliability. Why? Because when you run the test, when you run the reliability test, you'll know how many are failure, how many number of failures are there, how many are surviving. Right? When you run a test, what you'll understand, how many failures are happening, how many survivors are there. Correct? So when you do what happening? When you conduct a reliability test, what you are able to understand, how many are surviving, how many are failing. Correct? When you conduct a reliability test, you know how many items are success, how many items are failing. Yes or no?
Yes, sir.
But with respect to what? With respect to, as per the definition of reliability, with respect to what?
Time, sir.
Time. Excellent. So with respect to time. Next, once I know the lambda value, with respect to lambda t, what I can do? I can go for number of failures divided by number of survivors into lambda t. Correct? Okay, are you able to understand? If I know by doing a reliability test, I can know the when I conduct a test, I can know for failure rate of the particular product. Correct? Once I know the failure rate, what I can do? Once I know the failure rate, I can calculate the reliability at time t. Can you say the formula? Reliability at time t is equal to what? E power
Minus lambda t, sir.
minus lambda t. From where I will get this lambda t value? From step number
2, sir.
2. So that's why first you conduct the test, calculate the number of failures, number of survivors with respect to time t. Next you calculate the failure rate. Next you calculate the reliability. So this is a general procedure for doing a reliability. Okay. So I hope it is clear for you. Next, it's a test for you. Can you do the reliability test? Can you find the reliability of this? Reliability at t is equal to e power minus lambda t. This is the formula I know. Here, a trial data shows that 105 items failed during a test. So 105 means what? 100 items failed during the test. This denotes what? What is this value?
NF, sir.
It's called as NF. Very good. With a total operating time T equal to 1 million hours. T is what? 1 million hours. Find the reliability of your product after 1000 hours. Okay, total operating time is, so the total operating time is 1 million hours. That means what? The duration of the test is 100 million hours, but we can't do that many hours. So what they're asking us to do, assume for reliability at the time t. Reliability at time t is what? 1000. So you have to find the reliability when t equal to 100, 1000, when t equal to 1000. Do you know lambda now? Do you know lambda now? Only T I know. If I know lambda, I can calculate the reliability. Now you have to decide what is the T value, what is the lambda value. What is lambda value? So the lambda value is what? So first we have to calculate lambda value. If you know the lambda value, then I can put it in the reliability formula and I can calculate, correct? So let's find out the lambda value. Here lambda is what? 105, because it's given in the problem that for 1 million hours, what they're giving? For 1 million hours, 1 million is what? How many zeros? For 1 million hours, how many components are failing? When t equal to 1 million, number of fails is what? 105. So with this understanding, lambda is equal to n of f divided by t. I'm calculating. So I'm getting lambda value as 1.05 into 10 power minus 4. Now using this lambda value, I know reliability at time t is equal to, we have the formula, reliability at time t is equal to e power minus lambda into t. Lambda value, I'm substituting here, t at 1000 we are calculating, and we are finding that reliability as for 1000 items as for reliability at that time when time equal to 1000 hours is 0.9. That means what? 90% of the items are successful when time t equal to, when time t equal to, am I audible? When time t equal to 1000. Okay, so that's how we calculate reliability. So now let's enter into the other concepts. First is called as the mean time to failure. Okay, so what is this mean time to failure? Mean time to failure applies to non-repairable items. Okay, so non-repairable items means how many number of times the failure can happen. For non-repairable items, how many number of times the failure can happen?
One time, sir.
Only one time. Very good. So the failure can happen only once. So MTTF is defined as the average time an item may be expected to function before failure. Okay. So I'm buying a product, I'm using it. If it is, say for example, let's go to the old example. I'm buying a tire, I'm running it. Suddenly the tire got blasted. So I can't refix the tire and it becomes a non-repairable item now. So the failure can happen only once. So how long I am able to run with the product till the time it gets failed, that is called as MTTF, mean time to failure. Okay, so I'm buying a product, I'm using it. When t equal to 0, it is performing very well. Say for example, after some 1000 hours it has failed. So MTTF at 1000 is 0, right? Because it's no more useful for me. So MTTF is the mean time to first failure. MTTF can be estimated from a suitable example for of items which can be tested to the point of failure. So MTTF is the average of all times of failures. Okay, so say for example, of all failures of products, that is very important, because in products, I'm using the word products. Why? Because in MTTF, the failure can happen only once. Say for example, I'm buying four CFL bulbs. First bulb lasted for 400 hours. Second bulb lasted for 5,000 hours. Third bulb lasted for only 6,000 hours. Fourth bulb lasted only for 5,000 hours. So now, how should I calculate MTTF? It should be the average of all these values. 4,000 plus 5,000, 9,000, 9,000 plus 6,000, 15,000, 15,000 plus 5,000, 20,000. So 20,000 for how many bulbs? For 4 bulbs. So 20,000 hours divided by 4 will give me 5,000 hours. So that is the mean time to failure. That is the mean time to failure. Okay. So mean time to failure is only for which products or for which items?
Non-repairable, sir.
Non-repairable. Okay, and this MTTF is the average of all times of failure of the products which is used. Okay, good. Now, if you're having only a small sample, that is mean time to failure for small sample size, you can use this formula. Here, MTTF is what? MTTF is equal to 1 by n. N denotes the number of specimens. Ti is the time of failure for the ith inspection, that is the last inspection to happen. So that's when we use MTTF is equal to 1 by n, summation of n I equal to 1 Ti. So please note on this formula also. This is for MTTF is equal to small when MTTF is of small sample size. Say for example 10, 20 like that. When you have very small sample size, you can use this formula. Have you noted down?
Yes, sir.
When you have a large sample size, okay, you can use this formula. MTTF is equal to 1 by n, summation of n, k equal to 1, capital K nk into dot t, where n denotes the number of specimens, delta t is the time interval, nk is the number of failures during the kth hour. Okay, are you able to understand nk? That is, if I am starting from t equal to 0 to t equal to some 100, what is the failure at first hour? What is the number of failures at second hour? What is the failure at when nk is equal to 100? So all these things you are going to sum up. All these things you are going to sum up from last to last. Okay, so that's how we put k. K is a constant. Okay. Have you noted down this formula?
Done, sir.
So now let's go for the other thing, which is MTBF. We have this is called as mean time between failures. So mean time between is applies only for repairable items. Repairable items means what will be the number of failures? In repairable items, what will be the number of failures? It can be
So many times, sir.
it can be any number of times. So that's why we call as repairable items. So MTTF is for non-repairable and MTBF is for repairable. Okay. So MTBF is means mean time between failures. That means what? First I'm buying a tire, it's getting punctured, I'm fixing it. Again I'm running the using the tire, again it's getting punctured, I'm fixing it. Again running, again puncture, again fixing, again puncture, again running. Like this I can run this tire, use the tire for as many number of punches what I could make. Okay, between two successive component failures. Okay, but this time need not be equal. That is like, for example, I'm buying a tire today. After 1 month, I can get the first puncture. The second puncture can happen within 2 days. The third puncture can happen after 3 months. The fourth puncture can happen after 6 months. The fifth puncture can happen the next day itself. Are you able to understand? So the duration between failures cannot be predicted, need not be identical. It can fail anytime. But once it's failed, we should be able to fix the failure and able to run the machine or run the tire again. Okay, so MTBF is a function of time, and when system is operated, MTBF will fluctuate and then stabilize. Why? Because initially when your product is launched, the failures can be more, and after a period of time, the failures can stabilize or self-control, or it will be controlled again. Okay, say for example, I am buying a repairable product. Say for example, like a can you give me an example of any one repairable item? Any items which we can repair and use?
Bike servicing, sir.
A bike is there. Okay, a bike, for example, a bike. First, I'm buying a bike, and the bike has failed 4 times in a period of 2,000 hours. You are riding a bike for 20,000 hours. In the 20,000 hours, your bike has failed 4 times. Here, what happens? The first failure happened after 4,000 hours. After riding your bike for 4,000 hours, the bike has failed. After second, then you are repairing it. Then after 5,000 hours, the bike has failed. Then again you are repairing it. Again after 6,000 hours, the bike has failed. Then after you are repairing, you are running the bike for 5,000 hours, and again it has failed. So if you sum it up, the number of hours is 20, but the number of failures here is 4 times. So it is 20,000 divided by 4, which is equal to 5,000 hours. In the previous case, what happened? Here, 4 different products. Try to understand here, 4 different products failed at four different time intervals. Here, same product which has failed in 4 different durations. So that is the difference you should understand. You should be okay. Here, 4 same item, but 4 different times it has failed. Okay, but there it was 4 different items. Okay, so that is the difference you should understand. So to understand it better, now see, your system is on, that is off. Then you are running the machine. You are running the machine, and the machine is running for some time. And the failure, here this is the first failure that has happened. During failure, the machine is in downtime. So I made it like this. So this after this failure has happened, what you're doing in this failure time, what you're doing, you're trying to, if a failure happens, what you'll try to do, you'll try to
Repair.
repair. This is where your diagnose repair is happening. You're diagnosing what is the failure and you're trying to repair. Then the machine will start to function again. Then the machine will start to function again normally. This is called uptime. Then it will go run for a long time. Then after some duration, it will get failed. Then again what you'll do, you'll go for repairing. In this fail, when it is in downtime, you'll start repairing. Then again the machine will run and it will run. Then again it will going to fail. So the time between the time between these two failures is what we call as time between failures, or what we call as mean time between failures. This is what we call as MTBF. Mean time between two consecutive failures is called as MTBF. Okay, or it is a difference between up downtime and the uptime. The downtime and uptime. Say for example, here the machine has failed when t equal to 10, and here it is after some 30 hours. Again, failed, or 30 million hours has failed. So the mean time between failure is what? T of 30 minus T of 10. So mean time between failure is what now? In this case, downtime minus uptime, right? So what is the mean time between failure now? 30 minus 10?
20, sir.
20. So like this, if I'm able to calculate for all this failures, all this mean time between failure between all these failures, then so this is called as, sorry, one simple correction. So this is called as time to failure. Okay, this is called as what? Time to failure. And if I'm able to calculate this time to failure for all this number of failures what has happened, Then I call that as mean time between failures. Are you able to understand? Like this. Now t equal to 10. So after then the machine will start at t equal to 40. Then it can fail at t equal to 50. So now here TBF is what? Here it is 20. Here the TBF is what? What is the TBF here? Here 40, here 50. What is the TBF? What is the time between failure? Downtime minus uptime. What is the downtime? Are you able to understand? I'm in class, sir. I'll call you. Hello? 137. Hello? Am I audible?
Yes. Yes, yes,
Ah,
sir.
okay. Now tell me, when t equal to 50 and t equal to 40, what is the TBF? Like when t equal to 10 and t equal to 30, the TBF is what? Time between failure is what?
20, sir.
20. When t equal to 40, when t equal to 50 and when the downtime is 40, 50 and uptime is 40, what is the duration between this?
10, sir.
10, right? So mean time between failure for this two cases is 20 plus 10. Summation 20 plus 10. How many number of failures we have faced here?
Two
How many
times,
number
sir.
of failures? Two times. So 20 plus 10 is 30. 30 divided by 2 is 50. Okay?
50.
Okay. So that's how we should calculate mean time between failures. Okay. So now please note down this formulas. See, I want you to note down this formula. First note down this formula. Have you noted down?
Done, sir.
Okay. So now please note down these formulas. Okay. So here you see lambda is equal to 1 by MTBF, mean time between failure. Lambda is equal to 1 by MTTF. So by this both way, by using these both formulas, we can calculate the failure rate. MTBF for which component you will be doing, which items you will be doing? For
Yes, people, sir.
huh?
Repairable.
Yeah, for repairable. Okay. MTTF for what? For non non-repairable. Okay. For non-repairable, you will be using this formula. For repairable, you will be using this formula. Again, this equation can be slightly modified like this. Like MTBF is equal to 1 by lambda, MTTF is equal to 1 by lambda. Okay. Again, this is for repairable and this is for non-repairable. Okay. So are you able to understand? So please note on these two formulas. One for repairable and two for non repairable and two for non repairable. Two items are there. So MTBF is equal to 1 by lambda, MTTF is equal to 1 by lambda. MTBF and MTTF. Everything is 1 by lambda. Just remember how which is for repairable and which is for non repairable. Okay, done.
Done, sir.
Okay, good. So I hope you copied this formulas now. Okay. Yes. So now we'll see some introduction to maintainability, but this is not what is final, because we are going to see an elaborate discussion about a thing. But as part of this introduction module, introduction to reliability, we should know what is maintainability. Maintainability means which gives the chances for you to maintain your product. So that is what we call as maintainability. Okay, so maintainability means design for ease of maintenance. Okay, so for example, it's easy for you to remove a refill pen, and you can remove the refill and you can put a new one. It is easy for you to disassemble your tires from the vehicle, and easily you can do it. It is easy for you to disassemble a product, or it allows you to do the maintenance activity. You can easily oil your chains in your bike or in a cycle, and you can run it. So that is what it's easy to maintain. So whenever a system is allowing you to carry out the maintenance very easily, I call that as maintainability. Okay, so why you have to do maintainability? Okay, you have to do maintainability so that you're ensuring that the product can be retained or restored to a state in which it was functioning, right, under the stated conditions, using prescribed procedures and resources. I'll tell you one simple example. If you have the habit of riding a bicycle, if you have the habit of riding a bicycle, for example, if you have the habit of riding a bicycle, once your school days are over, in your summer holidays, what you'll do with the bike, you will do with the cycle, what you do with the people, what do you do with the cycle during your summer holidays? Are you listening to me?
Yes, sir.
When you're having a bicycle to your school, riding a bicycle to school in a summer vacation, what do you do with the bicycle? You will have the habit of giving that cycle to a cycle repair shop and doing the overhauling, right? Overhauling, what they'll do, they'll disassemble everything and assemble it back, restore it to the original state, and making the cycle to function to its original level under the stated conditions. You will do the assembly and disassembly using the prescribed procedures, which means what? That product is designed to carry out the maintenance activity. Okay, are you able to understand? Are you able to understand what is maintenance or maintainability? The cycle can be to do the maintenance activity of cycle. The cycle is designed to be or easy to be assembled and disassembled, disassembled and assembled together. When you are doing that, you are able to put some oil. You are able to correct the loose components, fasten the loose components, and do the correction activity, so that you are ensuring that your cycle will be similar to a new cycle. Correct? If not 100%, at least to the level of a new cycle, or to improve the performance of the old cycle, you will be doing that. So that is what we here I call as the maintainability. That means what you're able to carry out, it can be repair, renovate, remanufacture, or whatever it is. But what you're trying to do, you're trying to repair that product, or that there is repairing activities. What here I call as maintainability. If something is gone, you're able to fix it, and you're able to make the product to run it to its original state, or the state by following the protocols what has to be followed, then that is called as maintainability. Okay. Now, what is the mean time to repair? MTTR. Okay. Now we saw MTTF. We saw what is MTBF. Now I'm talking about MTTR. MTTR is the total corrective maintenance. Okay, total corrective maintenance. How many number of times you are able to do the corrective maintenance divided by the total number of corrective maintenance actions during a given period of time. Say this is about the hours maintenance time. Here it's about the number of corrective actions what you have taken, number of corrective maintenance what you made. Okay, so MTTR is total corrective maintenance time divided by total number of corrective maintenance actions during a given period of time. So please note down this formula. MTTR is total corrective maintenance time divided by total number of corrective maintenance actions during a given period of time. How many number of corrective maintenance activities you have carried out? Okay. How much is the total corrective maintenance time divided by how many number of times you have carried out the maintenance activity? That is called as mean time to repair. That is between downtime and the uptime. Okay, what happens when the machine is functioning? And after a period of time it fails. So the downtime of the machine starts, and after you repair, the product will again start functioning. Correct? That is called as time to repair. So let's go back. If you revisit this, you'll understand. So here what happens? Please focus on this slide. Here what happens when this is the downtime. Okay, this is when the downtime starts, and this is when the uptime again starts. Now this is what is happening here? What is happening here? Failure is happening. So this time is what is happening in this time? When a failure is happening, the downtime starts, and once the failure is repaired, the uptime starts. So what is happening here? What activity is happening here?
Repair, sir.
Repair. So this is the time to repair. This is what we call as time to repair. Say for example, in this case, say for example here the T is what? Here I mentioned T as what? In this point, what is the T value?
10, sir.
10 now. Here T value is what?
30, sir.
30. Here the T value is T equal to
40, sir.
40. So here what is the TTR value?
10, sir.
10. Let's assume that here T equal to 0. Here T equal to 0, here T equal to 10. What is the TTR value here? What's the TTR value here? T equal to 0, T equal to 10. What is the TTR value?
10 only, sir.
10 only. So mean time to repair 10 plus 10, 20 divided by number of times the repair activities happen. How many number of times the repair activities carried out here?
2 times, sir.
2 times. So 10 plus 10 is
20 divided by 2.
20 divided by 2. So the mean TTR value is how much?
10.
Mean TTR value is 20 divided by 2, 10. Okay, that's how we calculate mean time to repair. Okay. So now you can understand with this simple diagram what is mean time to. Okay, so here, so that's what we are. So mean time to failure is between two failures, how much is the time taken. So after this, you're diagnosing. So your time to diagnose, mean time to diagnose, mean time to repair, mean time to again. So this is what you have got. So this is what do you call this? So this is called as what? MTTR. But generally, MTTR also includes MTTD. This mean time to diagnose. This I didn't discuss because what is diagnosing? when a failure has happened, you're taking some time to understand why this failure has happened. So that is called as diagnosing. After diagnosing, what you do, you're trying to repair, you're finding a solution and trying to repair that. That is what is called as MTTD, and MTTD is the time taken for diagnosing. MPTTR is the time taken for repairing. And after you repair, again the machine starts functioning. So this will be your downtime, and this will be your uptime, right? So this is going to be uptime, and this is going to be the downtime. After that, the machine will again start to function. So empty time is mean time between failure. Between failure. So first failure and the second failure, what is the time duration? The duration between the first time of failure and the second time of failure, what is the duration? That I call as MTBF. How long it was running successfully, that is called as between two failures, how long it was running. So this between uptime and down, between first uptime and downtime, we call as MTDBF. Between this uptime and the next downtime, we call as MTTF. Okay, so that is what you have to understand. So now we have something called as maintenance corrective, because we are talking about corrective maintenance, right? So the actions which are performed when a failure occurs in order to bring back to, okay, it's called maintenance corrective. So normally this corrective maintenance is what we do normally in a simple, in a general industry, in a traditional industry, they do only the corrective maintenance. That is what, when something has failed, only after the failure you go to the machine, you repair the, you diagnose what has happened, you repair the machine and make the machine to function to its normal state or to the previous state. That is called corrective machine. Okay, for example, you got a fever. Okay, only after you get a fever, you go to the doctor, you get your fever diagnosed, you take some medicines to repair your body. So that is called as corrective maintenance. Are you able to understand?
Yes,
Only
sir.
after the problem has happened, only after the failure has happened, when you do some corrective measures, we call that as corrective maintenance. But assuming that you are going to have a fever, okay, because your body is not, you have body pain and other things which may lead to failure, you are anticipating a failure of your body. If 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 you're anticipating of your failure of your body, okay, okay, the climate is not good, suddenly the climate temperature has changed from cold to hot, it has suddenly went, so I'm feeling some uneasiness. So immediately I go to a doctor, I get my body diagnosed, take the preventive measures or antibiotics well in advance, so that the my body will be perfect and my body conditions will not deteriorate or failure. If I'm doing that preventive measures, like preventive measures before the failure is happening, if I'm doing something which can prevent myself from failing, that is called as preventive maintenance. Okay, so the actions which are performed as an attempt to retain an item in a specified conditions by providing systematic inspection, detection, and prevention of anticipated failure is called as maintenance corrective. Okay, normally we do know, you have a UPS battery in your home. What you do, then and there you inspect, and if you detect that level of that water is what you call as distilled water is low, you pour that distilled water and you ensure that the levels are same in your battery. So that is what you're anticipating a failure of that UPS battery. So in anticipation to that, you're doing a systematic inspection. That is at a regular time intervals. You do the inspection. You detect what is the mistake. Then you do the preventive measures. That's why it's called as preventive maintenance corrective. Okay, are you able to understand?
Yes, sir.
Okay, good. So next is called as preventive measures. Um, okay, so that's what next is called as preventive maintenance downtime. During the maintenance, whenever the preventive maintenance is carried out, the system is going to be put on hold or put on it's not going to function. So when you are carrying out the preventive maintenance activity, that time the machine is not going to function. When the machine is not going to function, we call that as downtime. So that is called as preventive maintenance. So that type of maintenance downtime is called as preventive maintenance downtime. Okay, say for example, your body is not functioning, you are anticipating something is going to happen, you are going to the doctor, you are taking the medicine, and doctor is advising you to take the rest. So when you are taking the rest to do the uh, corrective maintenance, like what you call as the preventive maintenance, so that is called as preventive maintenance downtime. Sometimes in your industry, like once in a month or once in a while, they shut down everything. They do the overall maintenance of the machines, and then they start run. So during this maintenance will be always here, not a corrective maintenance. It will be a preventive maintenance. Sundays, for example, on Sundays if you're not working, the Sundays all the machines are down. The maintenance team will carry out the maintenance activity on the Sunday, and ensure that from Monday, first shift, the machines are available for manufacturing. So this Sunday period, what they're doing the maintenance activity. This Sunday, when they do this maintenance activity, all the three shifts are closed. So that means what? The preventive maintenance, because of this preventive maintenance, there's a downtime of the machine. The machines are not going to function. So that I call it as preventive maintenance downtime. Okay. The next we have something called as mean time between maintenance. Okay. So mean time between maintenance is simple. So whenever you're doing, say this Sunday, you're going this Sunday. This is what today is, 2nd of March. 2nd of March, you're carrying out a maintenance activity in your company. Because of that, the machines are down. Then after some 20 days, say for example on 23rd of March, again you are going to carry out the maintenance activity. So the time between this, so today Sunday you're taking 1 day you're spending for maintenance activity. On 23rd and 24th you're doing the maintenance activity again. What is called the preventive maintenance you're going to do. So the time between these two maintenance is called as mean time between maintenance. So if during the calculation of MTBF, the preventive maintenance downtime is taken into consideration, then the value obtained is called as mean time between maintenance. Okay, mean time to diagnose, mean time to repair, and after repairing, what you're going to do, you're going to do the some maintenance. So mean time between maintenance. So this is also there. So MT, lot of MTD. First we started with MTTF, MTBF, MT. Then what are the MTs we have? So we saw from this, right? MTTF, we saw MTBF, we saw MTTR, then we know what is MTTD, mean time to diagnose. Then now we are looking into we know what is okay, PMDT we saw. Then we are looking into MTB, mean time between maintenance. Then we are going to see the next concept of supply downtime. What happens now? Supply is what? Supply of products, supply of items. So when you're doing a maintenance activity, what will happen? Your upstream activity will not be able to satisfy the demands of the downstream. Correct? You require something and you won't be able to give it to because the downstream activity is depending on the upstream activity. Correct? So when you have this type of condition, your downstream activity will be expecting the product from the upstream activity, and due to maintenance, this upstream activity will not be able to supply the product to the downstream activity. So because of this downtime, the supply is going to be down. Because of this maintenance activity, the supply is going to be down. So that's what we call this time duration when the supply is down is called as supply downtime. Say for example, there are two processes, A and B. Product B is dependent on product A, and in product A, that the machine where this product A is getting manufactured is undergoing some maintenance. Because of the maintenance, what is happening in the machine A, the product A after the product B will not be able to receive the product from the machine B, machine A to B. Okay, மிஷின் ஏல வந்து மேனுஃபேக்சரிங் மெயின்டெனன்ஸ் போயிட்டு இருக்குது. அதனால மிஷின் பிக்கு வந்து பொருள் வந்து போய் சேராது. அப்போ எதனால போய் சேரல? மிஷின் ஏ வந்து மெயின்டெனன்ஸ்ல இருக்கிறதுனால, ரைட்டா? ஸோ அப்போ மிஷின் ஏ மெயின்டெனன்ஸ்ல இருக்கிறதுனால அந்த மிஷின் பிக்கு வந்து ப்ராடக்ட் போய் சேரல. அதனால ஏன்னாவது அந்த சப்ளை வந்து கட் ஆயிருக்கு. ஏ டு பி அந்த சப்ளை வந்து கட் ஆயிருக்கு. ஸோ எதனால கட் ஆயிருக்கு? அந்த மெயின்டெனன்ஸ் ஆக்டிவிட்டி நடக்கிறனால. ஸோ இந்த சப்ளை வந்து கட் ஆனாலும் சப்ளை வந்து டவுன் ஆகுன்னு சொல்லுவோம். அந்த டைம் எவ்வளோ எடுத்துக்குதோ தட் வி கால் சப்ளை டவுன் டைம். Okay. Next, we have something called administrative downtime. This administrative downtime are very rare and it's very scarce in big companies. Administrative downtime, for example, the maintenance activities being carried out, or due to some external factors or internal factors, the supply of raw material can get affected. Okay, or say for example, due to lack of maintenance, proper maintenance plan, or say for example, tomorrow is Sunday, so 3rd March you are planning for some maintenance activity, and to carry out the maintenance activity, some items are required. But if due to some administrative reasons or lack in administration, if the maintenance activity cannot be carried out because of lack of some maintenance equipments which is required to carry out the maintenance activity because of some administrative reasons. This maintenance equipments are not arranged properly and the system is down because of that, then we call that as administrative downtime. To carry, I mean, again I repeat, to carry out the administrative, to carry out the maintenance activity, there are some maintenance equipments required. For example, if some maintenance equipments are required and this maintenance equipments are not arranged well in advance by the administrative people, because they may not be aware of this or something, or because of financial reasons or any other reasons, that there is a downtime in that is happening because of administrative reasons to carry out the maintenance. So that is what we call as administrative downtime. Okay. Then we have something called as actual repair time. Okay, so it's the actual time spent by one or more maintenance personnel to rectify a repair. So how much time the maintenance people are spending to repair a product or repair a machine. That is what we call as active repair. How much hours actually they are involved in repairing the product. This does not include the diagnosing time. This does not in some of the this does not include the maintenance diagnosing time. So without diagnosing time, only the actual time what is taken to repair the product, that is called as active repair time. Okay, then what is mean downtime? MDT. The statistical mean downtime includes supply downtime and administrative downtime. So if you are summing up the supply downtime and the administrative downtime because of maintenance what is being carried out, we call that as mean downtime. The summation of supply downtime and administrative downtime divided by 2. Okay, so supply downtime, mean of what? Supply downtime and administrative downtime is called as MDT, mean downtime. Then what is availability? Availability means operational readiness of the system. Availability is also put as the ability of an item to perform its required function at the state of time or overstated period of time. Availability is under combined aspects of reliability, maintenance, and uh, maintenance support. So that means what? Availability. That is, for example, today I want to manufacture some X product by using machine A. Okay, and this machine A should be available for me to produce the respected number of quantities of product X. Okay, so the availability of the product to manufacture the product X in the Y quantity is called as availability. Right? At any given instance, the machine should be available, and to ensure the availability, the machine should be reliable. It should be maintained properly, and it should be allowing me to maintain that properly. So that is what reliability, maintainability, and maintenance support should be there to ensure the availability of the machine. So availability means operation readiness of the system. You're having a car, and this, say for example, there's an emergency, a medical emergency in your house, and you are having a car, and this car should be available when it is actually in need. That is, the reliability of the car should be there. To ensure the reliability of the car, you should have carried out the maintenance activity correctly. To carry out the maintenance activity, that car should be maintainable. Okay, so that's why the reliability, maintenance, and maintainability are very much essential to ensure the availability of the car. So this car is available, that is operationally readable. That is, it should, if you put the key, it should start, right? So because that's an emergency situation, so that's why whenever the machine or anything is readily available to start the operation at any point of time, that is called availability. To ensure availability, again, we need the system should be reliable, maintainable, and maintenance support should also be available. Now, how to calculate availability? So we have something called as operation availability and inherent availability. Operation availability, I'm going to use the formula MTBF, mean time between failure divided by mean time between maintenance plus MDT. What is MDT? What is MDT?
Mean time to repair, sir.
Mean time to repair. It is a summation of
Time, sir.
what time? Supply downtime plus
Uptime, sir.
supply downtime plus what is ADT? Just now we saw because of administrative reasons. What do you call that? Administrative downtime. Okay, MDT is the sum is the mean of STDT plus ADT. Supply downtime and administrative downtime. Okay. So then inherent availability. Inherent means like it's already readily available. So it is MTBF, mean time between failure, divided by MTBF plus MTTR. So these two formulas, please memorize. Please note down these two formulas: operation availability and inherent availability. Have you noted down the formulas?
Yes, sir.
Okay. So next, okay, next is the important concept of hope my slides are visible to you now.
Yes, sir.
Thank you. So the next important concept which we'll be discussing about the concept of the bathtub curve. Okay. So what is bathtub curve? Have you seen a bathtub? I've seen a bathtub. Yes or no?
Yes, sir.
Okay, a bathtub will normally will be like looking like this, correct? A bathtub will be looking like this. Okay, since the curve is going to look like this, we call that as a bathtub curve. I will explain you with a in the next slide. So here what we are trying to do, we are trying to plot this curve between two things, one with x-axis and the other with the y-axis. This y-axis is about the failure rate. Okay, so how you represent failure rate? What is the letter we can use? What is the Greek letter you are going to use? What is the Greek letter you are going to use for failure rate? Look at the formula for failure rate. Failure rate is how will
Z or
denote
lambda.
it? Huh?
Z or lambda.
We can use Z or lambda. Then in the horizontal axis, I'm going to plot it against the time. When you plot the failure rate versus time, I'm going to get a bathtub kind of curve for any product. A bathtub kind of curve for any product. So that's why this is called a concept of it's called a bathtub curve. Okay, here we are going to have some three stages. First stage, second stage. So here this is the first stage, second, and this will be the third stage. Okay, this first stage is called as the infant mortality burn-in region or debugging region or break-in region. So normally it's called as the infant mortality stage. The second is called as the useful life or constant failure or service failures. The third stage is called as the wear out stage. Okay, so here if you see these things, here it will be more exponential, here it is going to be more of variable distribution, here it's going to be exponential distribution. Okay. Just remember this. In second stage of the useful life or the constant failure stage, it's going to be exponential. In third stage, it is going to be variable distribution. Just understand this. So this bathtub curve is plotted between what? Plotted between
Failure
what
rate
is in the
and
x
time.
axis and what is in the y axis? Failure rate and time. It has how many stages?
3 stages, sir.
3 stages. First stage is called as infant mortality. Second stage is called as useful life. Third stage is called as wear out. In second stage, we follow exponential distribution. In third stage, we will follow variable distribution. Almost this variable distribution can be used for all these 3 stages, but especially we can also use it for the third stage. Okay, what is it? How it is working? We'll see here. So this is, as I told you, this is for the failure rate. Okay, and this is for the time t. Whenever you are introducing a product, okay, whenever you're introducing a product inside the market, what happens in the early stages? The failures are more. Okay, here the failures are more. Then after a point, the number of failures will get decreased to a lower level, and the product will have a very good sales. And after some time, when after using a product for some time, the product will give some trouble and it will start to wear more, or the failures will happen more. Or understand? Initially, when you buy a machine, the machine will give some trouble in during calibration or during setup. Initially, it will be giving some failures, and after some time, it will be very working very well. And after some time, what will happen? Again, the after more where after running for a long hours, the maintenance will be more, or what do you call the chance of failure will be more here. Okay, so that's why in the early infant stages, decreasing failure rate. Okay, the failure rate will start to decrease, and in the useful life stage, that is in the stage 2, the failure rate will be constant, and towards the end, what happens? The failures will be more. For example, in a human life, when a baby is born, the baby is prone to more health issues. Okay, and still the time of some 6 7 or 8 10 years, the number of times we go to the hospital will reduce. Then from age of 10 to say some 30 40, the number of times we hospital will be almost once in a year or twice in a year. It will be very less. But after 40 or after 50, due to our lifestyle or something, the number of times we go to the hospital will get increased, because what, our body condition is deteriorating. To stabilize, it takes some time. To normalize, it takes some time. When it deteriorates, it takes more failures. So that's why the failures are decreasing, reaching a constant state, and again increasing. Okay, so that's why here we follow exponential distribution. Here we follow variable distribution. Okay, so this is the graph. So in this is called as infant mortality failure. That is, once the child is safe in the first stage, it can, okay, the failure rate will go on decreasing. Okay, when it comes to wear out failures, initially the wear will be less, but over a period of time the wear will be more. So when you want to plot a common line or common graph between infant mortality failure and the wear out failures, you end up making a curve like this. This curve is what do you call this curve now? What do you call this
Bath,
curve?
bathtub.
Bathtub curve. This bathtub curve is the curve which is plotted between infant mortality failure and the wear out failures. and the constant random failures. If you plot a graph between these three lines, infant mortality failure, wear out failures, and constant or the random failures, you end up making a curve, and that is the curve we call it as bathtub curve. Okay, are you able to understand this concept of bathtub curve?
Yes, sir.
And this is common for almost all products. Okay. So in infant mortality rate, this is what we have discussed. The failure rate is more, and it gradually decreases with the respective time. So over the time, what happens in infant mortality curve, the failures are reducing. Okay. Uh, okay. Why this can happen? Because when you buy a machine, there may be the welding can be poor, the connections can be poor, the contamination of surface in materials can be poor, or the polishing will not be proper. So there are some many reasons for a product to fail initially when it is released to the market. So that's why people always say, don't buy the product immediately when it is released in the market. Next, useful life. After reaching a useful life period, or after having more, after some 1 year, 2 year, the component is now used to the machine is now used to the operating conditions. Then it will start to function very well, and it will be running for a long, constantly. It will be running for a very long time. Then comes the burnout stage, where more maintenance has to be. Where burnout stage is like when it starts to get repair. Often it will get repair. Then you have to replace the components. You have to change the bearings, everything. So all lot of maintenance activity come out as the vehicle or the machine gets old. And it will lead to poor. This may be due to poor maintenance, or wear due to friction, wear due to aging, corrosion, creep, wrong overall practices, short designed in life of the product. Some products are designed to have very short, what do you call the second stage, the constant failure rate stage. It will be very. The product itself is designed to be like that. Best example, I think it could be our mobile phone. Okay, so just to explain you better, when you try to understand this. So when you buy a bike, for example, when you buy a new bike, initially the bike will get some time to adjust to your driving pattern. So it may cause some failures initially due to your bad driving pattern. After you're driving, after some time, what happens? The engine sets to your driving pattern, and the clutch gear, it's all set to your driving pattern, and the failures of this vehicle will be very less. But after a certain period of time, what happens? uh, you won't maintain it properly, you won't clean the vehicle, you won't do the oil lubrication, you won't give the engine oil, change the engine oil, you won't clean the filter. So because of all these reasons of poor maintenance and other things, driving pattern, what will happen after some time, say for after some 7, 6, 8, 7 years, the engine will give a lot of noise, the chain will not be working good, the vehicle can fail easily due to multiple reasons. So what happens after some 6, 7 years, the vehicle will start to give more troubles. So the failures will be more. So initially the failure will be more, but it will decrease, and it will be very constant. And after some time, the due to poor maintenance, it will be more. So that's why we were talking about availability. So availability becomes a question when you are not when the system is not reliable, when you are not doing the maintenance correctly, or if the system itself is not maintainability. If the maintainability is less, then this will lead to this increased failure rate, and the machine will not be available for you when you require it. That's what it calls availability. Okay, so hope you understood the concept of bathtub curve. Okay, so there are reliable. So if you want to talk about the mathematics or the statistical distributions behind this reliability, there are a lot of things. One is first is the exponential distribution. We have variable distribution. We have normal distribution, log normal distribution, and gamma distribution. So this is full of math, and I don't know how much you're going to take this. Um, but what I want you to do is just to note down few formulas to make it simpler. Okay, I want you to note down this formula first. So note on this formula, lambda of t is equal to ft divided by 1 minus ft, capital Ft. So ft denotes, do you remember what is this Ft? We saw a formula called as failure density. Okay, failure density divided by 1 minus cumulative distribution function, or the item failure probability at time t. So this is very important, Ft. Okay, Ft is what? Cumulative distribution function. This Ft can be written like this as what? Summation of t to z f of failure density with respect to change in time. Dt is what? Delta t. Dt is nothing but delta t. Okay, just note on this formula alone. Just note on this formula alone. In case if you want to calculate the hazard rate. Okay, have you noted down the formula?
Done, sir.
Okay. So next we have to, then the other way to calculate this hazard rate formula is this one. If you know the failure rate, how to calculate the hazard rate? Lambda t is equal to minus 1 by reliability of the component at time t into delta, change in reliability divided by change in time. Please note on this formula. This is one, that is proportion or inverse of reliability at time t. Reliability at time t 1 by reliability of time t into change in reliability at time t divided by change in time.
Done, sir.
Okay. Hazard rate for exponential functions, we have to see. This is in the logarithmic scale. Mm. Okay, I know that you have noted down this formula already. R of t is equal to e power minus lambda t. It's already done. Okay. Do you remember this sum?
Yes, sir. Remember.
Okay.
Much question.
I know you are very good at this, because everyone has already done this as part of your QC, quality control and improvement. QCI, you have done this same problem. I think you already worked out, correct? But today we saw how we worked out. Okay, you remember this, right?
Yes, sir.
Okay. So can someone share that screenshot which I shared? If you have this QCI screenshot for and solution to this formula, I hope one day I shared it, right? If you have that, can you reshare that? Someone, if you have that in our WhatsApp group, you can reshare the solution to this solution to this problem.
We'll share, sir.
Okay. Then I'm not going to touch upon this problem because the solution is already available to you. So how we calculated? First, we calculated the cumulative failures. We summed up in cumulative failure in accumulation, like 0 to 10, 1 to 10, 210 plus 143, 353, 353 plus 117, 470, like that we calculated. Then we calculated number of survivors. Okay, how many is the survivors? Yeah. Others, thanks for sharing. Okay, so the problem to this solution is already shared in our WhatsApp group. Okay, so you know this. So how to calculate cumulative failures, we know. So 1,000 components is the number of survivors in this given, already given 1,000 number of components is surviving. So we know how this is surviving. So number of surveys, how we will calculate. You can also check parallel, you can check your mobile phones and open our WhatsApp group to understand the number of survivors. Number of survivors, 1,000 is already given. 1,000 minus 210 is 1,000 minus 210, you get 750. 790 minus 143, you will get 647. 647 minus 117, you get 530. So like that, you will be able to calculate your number of survivors. How do you calculate number of failure density? Okay, failure density is what? Failure density is this 210 divided by 1000. Then we have to, like this, you have to calculate 210 divided by 1000 and 143 divided by 1000, 117 divided by 1000. Like that, you have to just number failure, like this, f divided by fd. F divided by fd, you will get failure density. Then how to calculate this average average population? Average population, how we are going to calculate? 1000 plus 790. Okay, 1000 plus 790 divided by 2, you'll get average population. 790 plus 647 divided by 2, you'll get 718. Okay, then how we are going to calculate failure rate? Failure rate is f is what? 210 divided by average population. So 210 divided by 895. 143 divided by 143 divided by 718. So like this, you will get the failure rate. So once you know the failure rate, that is Z, you can calculate the reliability. Z or lambda. Failure rate is Z or lambda. If you use that, lambda or what you call e power minus lambda t. But you can calculate that, or you can, what you can do is, we also know that when you know the failure rate is going to be it's going to be like this. For the first case, it will be 1, and the last case is going to be 0. That we already know. But how to calculate this 790? It is like s of I divided by s of I divided by s naught. That is 790 divided by 1000, 647 divided by 1000, 530 divided by 1000. So it is like that. Also, we can calculate the reliability. Then you, for able to calculate all this average, how to calculate the mean failure rate? Calculate everything divided by 10. You will get mean failure rate. Okay, so that's how we should do this formula. Since I have explained this formula already very well, and the solution is also provided through our WhatsApp link, I'll just walk you through this problem. And others, thank you for sharing this. Hope you had the backup. Okay, so now let's do this problem. Determine the MTTF for a mission time of 1000 hours. Okay, MTTF is what? Mean time to
Failure, sir.
failure. How many hours is this machine is running?
1000 hours, sir.
1000 hours. 10, how many number of components they are testing? 10 components they are testing. So now you have to find the reliability of the components. You have 10 components. You have total number of failures is 807, 820, 810, 875, 900, 837, 850, 790, 866, and 815. So how will you calculate the MTTF? MTTF, what is the formula? Is going to be the summation of mean time to failure. You have time to failure. Time to failure you have to calculate mean time to failure. First you have to calculate the MTTF. Then you have to calculate the reliability. First you calculate the MTTF. You have to sum all the time to failure divided by you tell me, divided by 10 or 1000. Then you will get the mean time to failure. Then once you get the mean time MTTF, MTTF is equal to 1 by MTTF is equal to 1 by
N, sir.
N. You have to find the reliability, right? Lambda is equal to 1 by, or the other way, lambda is equal to 1 by you written the formula, right? I asked you to write for repairable, non-repairable, 4 formulas you wrote. MTTF is equal to 1 by lambda. Lambda is equal to 1 by MTTF. You remember? So using that, we are going to solve. So now this is for large sample. Okay, 10 samples. So now, or for this was small sample. So that's what simply you what you're going to do, you're going to add all these things and divide it by 10, because this is time to failure. Now we have to kind mean time to failure. So mean time to failure means what? You have to add everything and divide it by 10. You'll get MTTF. Once you get MTTF, you know lambda is equal to 1 by MTTF. You're going to substitute 1 divided by 837. You're going to get failure rate. Lambda you can get. Once you get lambda, again they're given T is equal to 10,000 hours. You're going to substitute T equal to 1,000 hours. So you get e power minus lambda is 0.0012. T is 1,000 hours. So e power minus lambda T is 0.0312 or 30.12 percentage. Okay. Are you able to understand this formula, this problem? Is it easy? Do you want me to explain again? Anything, yes or no?
Understood, sir.
Okay, good. Next, this is another case. The life study data of 1,000 specimens of a particular device are shown in table. Determine MTTF of the device for an operating period of 10 hours. Operating time is 10 hours. And for this, they're going to ask you, like say for example, when t equal to 0, 0 to 1,000, 0 components are failed. 1,000 to 150, 1,050, 175 is failed. 150 to 1,100, 400 is failed. 1,100 to 1,150, 300 is failed. 1,150 to 1,200, 120 components have failed. So between these five different durations, how many number of components failed, that details they are given. Okay. So now what you have to do, now this is a large sample. So what you can do is here, okay. So here what you are doing, you are going to take this and you are going to multiply. So between 175, that is first case no problem. So for the second case, 175 into 1,050, because 1,050. This is the duration, right? So 1,150 at the kth hour, there is a 1,000. When 1,050 is there, what is the number of failures? 175. Okay, so once at 1,050 at hour, 175 is failed. At sorry, at 1,100, 400 is failed. At 1,150, 300 is failed. At 1,200, 125 is failed. So that's what you're doing. And how many number of hours totally? 1,000 hours. So for 1,000 hours, we are calculating the MTTF. Just direct substitutions only. Only the problem looks bigger in reliability. The solutions are very, very simple. Just direct substitution into the formulas. Okay. The next problem is the failure rate of a component. Failure rate is given. That is what lambda is given. And reliability, determine the R you have to calculate. R of T at T you have to calculate. And the MTTF for, and you have to calculate the MTTF also. So these two things you are both supposed to get. T is given as 100 hours. So directly you can substitute and find out. Then again the failure rate is given, lambda. What is the reliability of the component of the operating on this T? So this is very simple. E power minus lambda T, R of T. Okay, you substitute and you can find it out. Same way, reliability of component operating time T is given, failure rate is given, number of components is given. Then after T, that is when T is equal to 200, what is the reliability? So R of T equal to 200 is equal to e power minus 0.4 into 10 power minus 5 200. Substitute that, you will get the answer. Okay, so thank you. So here we are completing the first module of your course. Okay, so now if you have any questions, I can take it out. Okay. So if you have any questions, I can take it.
No, sir.
Okay. Okay, then I'm stopping the recording here.